All right, so this is the second video on area between curves for AP Calculus section 7.2 in your textbook. So we're going to pick up with example number 4. Here we want to find the area of region R, which is the whole region bounded above by the curve y equals the square root of x and below by the x-axis as well as by the line y equals x minus 2. So in this picture here, everything that's shaded makes up region R. But notice that in the picture, it has been divided up into this gray region A and the blue region B. The reason that that has been done is because if you think about how we find area between curves, we do upper function minus lower function or outer function minus inner function. Well, for the gray portion, region A, the curve y equals square root of x is the outer function and the x-axis is the inner function. So for region A, the area would be the integral from 0 to that pink line, which is at x equals 2, of the square root of x, technically minus the x-axis, but that's just y equals 0. So we don't need to subtract anything. So that's how we would find region A. For region B then, that is bounded above by the curve square root of x and below by the line x minus 2. So for region B, his area is going to be the integral from 2 to 4. We know that it's 4 because they marked it on the graph for us, of the square root of x minus x minus 2. So what we're going to have to do to find the entire region is to break that up. We have to find the area of region A and then the area of region B, and then we'll put them together. So for A, I'm going to rewrite that as x to the 1/2. Then we can work backwards. That becomes 2/3 x to the 3/2 from 0 to 2. So we have 2 to the 3/2 minus 0 to the 3/2. So 2 to the 3/2, if you want to think through what that actually is, remember we do the denominator first, so that would be the square root of 2, but then that would be cubed. So that's the square root of 2 times the square root of 2 times another square root of 2. So that would end up being 2 square roots of 2. And then this next part is just 0. So we end up with 4 square roots of 2 over 3 for region A. Then for region B, I am first going to rewrite the square root of x, and then I'm going to distribute my subtraction there. Roll that up some. So we know that x to the 1/2 becomes 2/3 x to the 3/2, then minus 1/2 x squared plus 2x from 2 to 4. So that would be 2/3 4 to the 3/2 minus 1/2 4 squared plus 2 times 4 minus 2/3 2 to the 3/2 minus 1/2 times 2 squared plus 2 times 2. Okay, so again, 4 to the 3/2, you do the root first, so that would be the square root of 4 is 2, 2 cubed is 8, 8 times 2/3 is 16/3, then minus 4 squared is 16 times 1/2 is 8, and then plus 8, and then minus the next piece. Now I already know what 2/3 times 2 to the 3/2 is because I had to find it for region A. It is 4 square roots of 2 over 3. The next piece would be 2 squared is 4 times 1/2 is 2. Notice that it's negative, but we're subtracting that whole piece, so that becomes a plus 2. And the next piece would be a plus 4, but since we're subtracting all of that, it would be a minus 4. All right, looking at all that, your minus 8 and your plus 8 cancel, so you end up with 16 minus 4 square roots of 2, that's all over 3. And then 2 minus 4 would give me a minus 2 here. So we get 16 minus 4 square roots of 2 2 would be the same as 6/3. So I'll put a minus 6 right there. So we end up with 10 minus 4 square roots of 2 over 3 for region B. So region R is A plus B. So it would be 4 square roots of 2 over 3 plus 10 minus 4 square roots of 2 over 3. Thankfully, it all has common denominators, so we just pay attention to combining the numerators together. Notice the 4 square roots of 2 cancel each other and all that radical work, and we get 10/3 for the total area there. Now, I'm going to, well, okay. So what if we change our perspective a little bit? Nobody really said that we had to always do all integrals with respect to x. So what if we integrated with respect to y instead? Here, for example, it says determine the area of the region enclosed by x equals 1/2 y squared minus 3. So that's that red parabola that opens to the right. And then the line y equals x minus 1. That's the blue line. So if I want the region enclosed by those two things, that is all of this. And if I was going to do it with respect to x, then if we think in terms of upper minus lower, we would actually have two regions here. This left region, the curved portion there, that would be bounded by the upper portion of the parabola and the lower portion of the parabola, which if we were thinking of it in terms of x, that would mean that we would have to take this x equals 1/2 y squared minus 3, and we would have to put it into y equals form. That would require square rooting, and when we square root, we get a positive square root and a negative square root. So the positive y equals square root would give us the top part of that parabola, and the negative square root would give us the bottom part of that parabola. So that would require integrating those two parabolas. It would require u substitution. It would get ugly. And then for the right-hand side, this kind of triangular space, that would be covered by the upper portion of the parabola, so the upper positive square root in terms of y, and then the line y equals x minus 1. So again, that would require two sets of integrals to do that problem. So what if we didn't think about it in terms of x? What if we thought about it in terms of y? Well, if you think about it in terms of y, that really doesn't change a lot about your process. Your process is still going to be to integrate outer minus inner. So here we would take the function that's the farthest to the right. Instead of the farthest up, we think about the positive x direction would be the farthest to the right minus the function that's more towards the left. So the parabola is the one that's more towards the left. The line is the one that's more towards the right. The only thing is, though, is that I'm integrating this with respect to y. So that means my integral will have a dy in it, which means all of my equations need to be written in terms of y. Well, that's all well and good for the parabola because it's written in terms of y. The line, though, is not written in terms of y. I need it to say x equals blah, blah, blah. Luckily, though, that's easy to do. And the line is x equals y plus 1. So if I'm going to do my right function minus my left function, that's what it would look like. Now, the other thing that we have to pay attention to are our boundaries. If we're integrating with respect to y, then your boundaries are going to be y variables. So that would go from the lowest point to the highest point. So this is down here at y equals -2. This is up here at y equals 4. So my integral will go from -2 to +4. All right, so I want you to try the math behind this now. I've talked about setting it up. I want you to practice actually doing the integral. So pause the video, integrate this, and let's see what you end up with. All right, so check your math with mine. Notice I didn't change anything about my process just because I was using y variables instead of x's. I still think through the reverse power rule and all that the same way that I've been doing it with x's for quite a while now. And so hopefully you ended up with positive 18 for the area of that entire teardrop region. So now let's kind of shift perspective. Let's go back and look at number 4 again, but let's do it in terms of y instead of in terms of x there. So if you look at that region again, I'm just going to kind of roughly sketch it. I should have put the picture up here again. So I've got this going on basically. This is the curve y equals the square root of x, and this is the line y equals x minus 2. Well, thinking about it in terms of x, I had to chop it up into 2 regions like we did in example 4. But if I think about it in terms of y and right function versus left function, this y equals x minus 2 is always the right side boundary of this whole kind of shark fin shape. And then the curve y equals square root of x is always the left-hand boundary of that region. So that means that in terms of integrating, I could integrate with respect to y and just do the line minus the curve. The only thing is, though, these have to be in x equals form in order to integrate with respect to y. So this one is easy to do, x equals y plus 2, so that would come first. And then this one, to get it in terms of x, we would square both sides. So we would get y squared equals x. So x equals y squared like that. Now our boundaries, they have to be y values. So my lowest y value is right here. That's at 0. My highest would be right here. And if you go back and look at the original picture, they told us that that was the point 42. The y coordinate there is 2. So that's what I want to use. So again, I'm going to have you work on practicing your integrals. So I want you to pause the video again and see if you can get the answer from here. So if you think about it, you should have already known what this answer was, because changing our perspective does not change the amount of area that's in there. We already knew what the answer was because we had found it back in example 4. It was 10/3. So hopefully you got 10/3 yourself. If not, compare your work to mine and see where we kind of went different ways. All right, so that wraps up then area between curves. You've got an AP practice problem there down at the bottom of your notes. Give it a try, and we'll talk about it the next time that I see you.